Y,
M,
M,
S,
S,
A,
A,
I, C,
C,
T,
T,
R.
R.
We are Team B5, 18500 Spring 25, and our project is Enigma 18. Our project is to recreate the Enigma machine, a historical cipher device used by Nazi Germany during World War II and famously deciphered by the British at Bletchley Park. It uses a rotor system that changes the encryption each time a letter is typed, while shared daily settings allowed both the sender and receiver to configure their machines identically, ensuring secure communication. Our implementation is modeled after the Enigma 1 model from 1930, following the exact encryption settings as the original. We plan to distribute this as an educational tool to help users learn about the history of cryptography. It's designed for use in museums and classrooms, so it has to be compact, modular, and interactive. We also plan for it to be open source, so it can be accessible regardless of access to technical institutions. The Enigma machine is an electromechanical cipher device. That means it uses both electrical circuits and moving mechanical parts to scramble letters. When you press a key on the Enigma's keyboard, you complete an electrical circuit. That current flows through a series of rotating disks called rotors. Each rotor shifts the signal based on an internal wiring pattern. The signal passes through 3 of these rotors and then hits the reflector, which bounces the signal back through the rotors in reverse, resulting in a symmetric encryption. Finally, it lights up a different encrypted letter on the lamp board. Each rotor has several settings: rotor number, which rotor you use out of set of 8, starting position, what letter each rotor starts at before you type, and ring position, the position at which the rotor causes the next rotor to rotate. Together, these settings create a large number of possible configurations, about 1 million in our replica, making it extremely hard to crack without knowing the exact setup.
To recreate this behavior, we used an FPGA. This acts like a blank circuit, allowing us to rewire our design through code. This allowed us to find a middle ground between a purely software modernized Enigma emulator and the original circuitry. We used the DE10 standard FPGA, and we used the Verilog hardware description language. Our FPGA handles the entire encryption process. It stores the rotor wirings and rotates them with every key press, just like the original Enigma. The mappings are hard-coded onto the FPGA itself. Now let's talk about how we built the peripherals, which gives our product more of an original look and feel. We take our input from a regular PS2 keyboard through the PS2 port on the DE10. We were able to source this keyboard through Facebook Marketplace. The legacy PS2 protocol includes 1 start bit, 8 data bits, 1 parity bit for error checking, and 1 stop bit. The finite state machine is able to decode the signal from the keyboard and feed each letter to the FPGA's encryption circuit. One challenge we faced was integrating the PS2 keyboard with our encryption logic on the FPGA. The keyboard runs at a slower clock frequency than the DE10. In order to sync both clocks and ensure 100% encryption accuracy, we limited the expected typing speed to around 100 characters per minute. While this is slower than typical typing speeds, it fits the intended use since users will naturally pause after each key to observe the encrypted output. To adjust the rotor settings, we used a rotor encoder, just like how the Enigma machine rotors would need to be configured. Through 2 signals on the FPGA, we are able to detect when the knob is turned and what direction it moves in, allowing us to change our rotor settings from A through Z and 1 through 8. We show the rotor positions on 7-segment displays using a MAX 7219 chip. It communicates with the FPGA through SPI protocol, a serial protocol that allows us to control multiple displays at once. To light up the output letter on the lamp board, we use a set of shift registers. These let us control the 26 LEDs on the lamp board with just a few pins from the FPGA, which is important since we only get 36 GPIO pins to use on the DE10. Here is a top-level view of our entire design from plain text to ciphertext using the rotors and reflector.
Now we can take a closer look at our PCB, which is a custom-designed printed circuit board. This brings our hardware and peripherals together for an integrated solution. We designed the interface to emulate the look and feel of the original Enigma machine. On the left, you can see the interface of the original Enigma, with its rotors, lamp board, and keyboard. On our right, our final PCB layout brings those same features into a modern Enigma embedded solution. The rotor encoder lets you rotate through different rotor values. By holding one of the selection buttons and twisting the encoder, you can switch between rotor number, starting position, or ring setting.
The 7-segment displays show the current settings of each rotor in real time. On the lamp board, the output letter lights up when you press the letter on the keyboard. It is not in the typical QWERTY format, it's actually QWERTZ, just like the original Enigma machine. Finally, we use a PS2 keyboard to type the input. A key press sends a plain text and ciphertext to be displayed on the 7 segments. We started with designing a schematic in Fusion 360. A challenge we had was selecting peripheral components that were all compatible with 3v3 supply voltage, since the DE10 FPGA operates on 3v3 logic. From there, we moved to PCB layout. Here, we carefully placed and routed every component. Key design decisions included keeping related components like shift registers and LEDs physically grouped, as well as clear silkscreen labels for easy user experience. We also made sure to have wide trace length for manufacturability. Then we received our bare PCB and stencil from Oshpark, and we could begin assembly. We started by preparing the board and applying solder paste using a stencil. This ensures that only the right pads receive solder. Next, we placed the surface mount resistors one by one, using tweezers. After everything was in place, we carefully baked the boards in a reflow oven. The heat melts the solder and secures the parts permanently. Once reflow was complete, we moved on to the through-hole components that were hand-soldered, like the rotary encoder, buttons, and headers for connecting to the DE10. You can see our full assembly here, combining our PCB, FPGA, and custom laser cut housing.
Here's the final demo of our entire system working. First, we can set all the rotor settings using our rotary encoder and buttons. Let's set rotor 3's starting position to be E, rotor 2's ring position to be J, and rotor 1's starting position to be B. Now let's encode Hammy. We can see the encrypted text light up on the lamp board, spelling DKLHR. To decrypt this, let's first try it on an online simulator. We've set the rotor settings to be the same as our encryption settings. Now try DKLHR. That reads Hammy. Now try it on our machine. Reset the decryption settings to be E, J, and B. Entering DKLHR gives us Hammy once again. Special thanks to Sam Lemley, Curator of Special Collections at CMU Libraries, our advising faculty Tamal Mukherjee, and advising TA Ankit. Thank you.